Okay, let us start the lecture for today. First of all, we recall what we have went through last week. Last week, we saw if we are given the transfer function, then we know the methods to construct the state space equation. So it means that if we are given g of s, the transfer equation, right, then we can arrive at the time differentiation of the states x with the system matrix, and then the gain matrix, and then the input. Now we try to take a look, right, the equivalence between the transfer function and the state space equation. That is, if in this case now we are given the state space equation. We want to know what the control system will respond. Then we have to revert back to the transfer equation. Okay, and then the method to do it is quite straightforward. So the way to do it is that from the brief description of the procedure, we treat the state variable the x, then the x dot, right, as Laplace transformable. Then we go back to the Laplace transform of the state x differentiator against time. Okay. Then the transform is, right, if you look back to your Laplace transform table, the differentiation is a multiplication with the s variable and then subtract the initial condition. So this part is the initial condition. So we assume x0 equals 0. Then we have the s of x, so it equal to, on the right hand side, and then A and B are constants. Okay. So it is not transformed. Then we put the A multiplier of x Laplace transformed to the left-hand side. Then we have the Sx minus A of xs equals B u of x. And then E equals Si minus A. Here are the I. Okay, it is unity matrix. It's a diagonal element. All equal to 1. Then the state variable equal to the inverse multiplier of B of US. So that is to say, the input and then it is the x of s is the state. So it affects the state according to the matrix B. Of course, we have the U of S multiply the matrix B, the vector B, and then most importantly, it is the inverse of Si minus A. And then the A here is the system. Okay, this is a little bit counterintuitive, right? It is the inverse of the system. But this is what the mathematics derived tells us. So it is so, right? Now we'll also look at the output. And then we define the y of s, c, and then xs. Okay, c is a matrix. Then we have a y of s equals c, and then x is s minus a inverse b, and then u has. And then the transfer function is the g of s equals y, and then the output divided by the input, and that is the transfer equation becomes c is I minus a inverse, then b. okay up to here? Any question? Is that okay? Okay, then let us look at an example, right? Example. So suppose we are given a equals minus 3 and then minus 2. Some easy numbers to calculate. Right? So if we are given this, then we do the calculations step by step. Now, the first step is Si, so it is S. Okay, so it is S. Here, I is defined as the identity matrix or the identity of 2 by 2 dimension, because A is 2 by 2 dimension. Okay, the next step is I minus A. So we have S minus A. The given matrix in this example, this. So it equals S plus 3 and 2, then minus 1, and it's this. Okay. Okay. Then we continue, and then we find out the inverse. So first of all, we find out the minor matrix. Okay, remember how to find the minor matrix? Okay. We, in the first row, first column element, we cross out the first row, and then we cross out the first element, first column, and then the remaining element is the S. Okay, so we have the minor matrix. It is S and minus 1, and then 2 S plus 3. Then we have the cofactor. So the cofactor is the minus 1 to the power the row index plus the column index. So it is 1 and then minus 2 and then S plus 3. And then the adjoint matrix, okay, it is the transpose of the cofactor. So it is equal to then S and then minus 2, 1 S plus 3. So those procedures that we have went through in the revision for the matrix algebra, right? Then we also find out the determinant. So determinant of the of this matrix. So we have the northwest to southeast diagonal the product, and then we subtract the product of the northeast to southwest diagonal elements. So it is S plus 3 multiply with S, and then subtract minus 1 multiply with 2. So it is A squared plus 3S plus 2. So this is the determinant. This one, we find out the determinant of this matrix. Determinant, we find it out from this. So it is the determinant of Si minus A. Okay. So we have the inverse. So it is adjoint divided by the determinant. So the adjoint is S minus 2, 1S plus 3, and then S squared plus 3S plus 2. Okay, any question up to here? Is that okay? Then we calculate the RGS equals C is I minus A inverse, and then B. So it is equal to 1, 0. And then the inverse, and then our B matrix, and then divide by the determinant. So we calculate the C multiplied with the middle matrix, right? The first term is 1 and the second term is 0. So it takes only the first row. So this one takes only the first row. And then on the other hand, if we multiply with the B matrix, okay, then we have this, because this the upper element is 0. So we have the 1 only. So finally, the transfer function is the determinant 1. So for this example, right, we have this transfer function from the state space equation. Okay, see, any question on this example? Is that okay? So what we can see from this example is that what So what we can say is that we have an observation. A state space equation. It is related or equivalent to the transfer function. And then in particular, or the important point is that determinant of Si minus A, okay, is the denominator of the transfer function. And then we also know that because it is the denominator of the transfer function, right, so it determines the behavior, right? It determines the behavior of the system. Okay, it's under control. And one more thing, it is the most important thing is that if determinant equals 0, so what it means is that the transfer equation cannot be found, okay, because it's determinant is the denominator. If the denominator is 0, then the transfer function just goes to infinitive, right? It means that the system cannot be controlled. Agree? Okay. So any question up to here? Is that okay? And then on the other hand, the system matrix okay, can infer the system response and then in our example, we have the determinant equals a squared plus what? 3s plus 2. So if we factorize, then we have s plus 1 and then s plus 2. And then because these factors are in the denominator, then the response will contain terms in e minus t and then e minus 2t. Okay, that is from inverse Laplace transform. So because this determinant is calculated by, it's calculated only related to A, right? And then if we can do the inverse Laplace transform, then we must have some terms, the exponential minus t and the exponential minus 2t, according to the poles of according to the solutions of the S variable, this two solution, right? So the conclusion is that the system matrix can infer the system response. Okay, any question about this observation? Okay. So now we know that the A matrix, it affects the system response. And then actually how it affects. So how actually it affects. So we take a look at an example. We have a water tank system. The water tank system is like this. So we have the area, the cross-sectional area A1 and then A2, and then the height of the tank 1 is H1, the height of tank 2 is H2, and then we have a resistance of flow R1, and then the outlet pipe resistance R2, and then if we have the input Q, the flow rate input. So first of all, we set up the differential equations. Set up model by differential equations. So we adopt the principle of balancing the input output flow rate. Okay, it is similar to the fact that the input we pull in water into the tank 1, and then if those pipes are not blocked, right, eventually the water level will be balanced. So for tank 1, the input will make the water level increase. So the area in the tank make it increase. And then it is also because of the resistance here we can say that it is the net water volume increment rate. Here is the water inlet rate, and then this one is water leakage rate. Yeah, okay, see this? Oh, sorry. Okay, because we have the water inlet, right? The effect of pumping water into the tank 1, it will increase the water level, and then it also causes a drained leak outlet, right? From tank 1 to tank 2. Okay, any question up to here? And then for our tank 2, and then tank 2, the increase of the water level, it is the inlet. And then subtract with the outlet. So it is rate of water level. And this is inlet from tank 1 to 2. And then it is leakage rate. Okay. And then we try to write the states, okay, and then we define the states. defined states is H1 and H2. Okay, because we are interested in the in what levels. Then rewrite the equations. You write the equations. We have the H1 time derivative equals minus 1 A1R1, then H1 plus then H2 A1, then the inlet rate. Then we also the H2, the water level of tank 2 equals 1 minus, subtract by HR 1, then H1 minus 1 of A. So any question up to here? Is that okay? Then we set up the matrix equations. So we have all the differentiations on the left-hand side. And then we substitute or rewrite the previous two differential equations into the matrix form. Right. And we multiply H1, H2 variables. And then the first one is minus 1 divided by A1R1, and then 1 A1R1 multiplied with H2. And then here it is ATR2, and then minus 1 A2. And then for the control, it is 1 over A1, and then it is our control inlet Q. So which is in the form. So we have the x vector differentiated equals a of x plus b and then u. So then we can define the if we let any numerical value, right, a1 equals 1, then a2 equals 1, r1 equals 1, and then r2 equals 1. That's any numerical value. Then we have we have a equals this one, the first row, first column element. All the numerator and denominator are 1, but with the negative sign. And then we have b equals 1 and 0. So for interest of control, So if wanted, is wanted water level on tank 1, then the output is Y1, okay, it is 1, 0, and then the H1, H2. So it is, we have a Y equals Cx. Okay, similarly, if wanted and to tank 2, then the output is this Y2 equals 0, 1. And then with H1 and H2, it is also in this form. So we have the same form, but different C matrix. Okay. Is that okay? Up to here, any question? So what we can see here is that, okay, the state space equation can be obtained directly from differential equations. And those differentiations are described equations describing the physical phenomenon. And then, of course, from the state space equation, okay, then can, if required, convert a state space equation to transfer function. Okay. The conversion is what we have discussed right earlier this afternoon, making use of the matrix inversion. Okay, any question up to here? Okay, if no, then we take a short break and then we continue with the other topics.
Just to get a bearing on this, last week when we went through those three, to be honest, quite long methods of solving for that, the state space equations from the transfer function, are you saying that if we had a question and it said from the transfer function find the state space equation, it would be better to convert it into a differential equation and then find the state space equations directly? Is that
the answer is yes or no, right? If we are given a transfer equation, right, so we better try to identify the integrators and then use the block diagram method to find out the state space equation.
right?
Here, this afternoon, we we see that from the physics of the problem, right? The water flow, right? This is the physics. We have the set of differential equations. Right? From the set of differential equations, we can either generate the transfer function, or we can obtain the state space directly.
Right, because I'm asking because in the tutorials, like I'll just show you here. I think this is the one. In the tutorials, we never went over anything involving something where, like, we never had in the tutorials, we don't have any examples where we start with a transfer function, go through to find the block diagram. Like, we don't go through this process in order to find the state space equation. In none of the tutorial problems we do this. So, are we expected to follow this procedure in a question? Because even though you said that it's very highly dependent on the question itself and very unique, and there are probably like a very large amount of probable solutions for the transfer function.
I think the best way to look at it is that we have a problem, a control problem to solve, right? But we have different approaches that can solve the same problem.
Right. So in an exam, when we have, considering it's a timed exam, and this year it's only 2 hours instead of 3, this would take a very large portion of time to put, like, to put.
Okay, for the examination, maybe next week we will have a revision. What will be expected in the examination.
Oh, okay. And would we talk about whether this sort of question, like,
It's difficult to
I know
tell.
you can't say the exact question, but, you know, like, maybe if there's some sort of practice example that those things. Right.
I was just wondering, you said the page limit for the assignment is 10 pages. Does that include the appendix?
Do we need an appendix to
Just because I've got a lot of graphs and my reports ended up being about.
the graphs, you can put in the 3 graphs in a row.
Yeah, I've done that stuff, but my reports, it's over the limit, and I'm wondering if I can just put.
The importance is that the system, right? The Moodle system. You cannot put 5 gigabytes up, right?
Yeah,
There's
but
a
like
limit
the
there.
page, like my report's
The
quite.
page limit doesn't matter.
Oh, it doesn't matter. So you said it was 10 pages, but if it goes over, is it
10
okay?
pages is reasonable, right?
But I've gone over that already. So is it?
11, 12.
It's probably going to end up being 12, maybe a bit over 12, with an appendix though.
Yeah, that's
Because I've got like
reasonable.
like with figures in the appendix as well, so it's probably
that's
all up about
reasonable.
14 and a half. Is that okay?
Okay.
And I'm not going to get like marked down or anything?
No.
No? Okay.
Definitely not.
Okay, good. Thank you.
For this assignment, like for this part, the equations that we get is like a really big differential equation, derivative, and then like we have like omega to the power of like 6.
Sorry.
Like when we find the modulus to find omega p, and then we differentiate it to find the maximum, we get like a very big. I get a very big derivative. It's really complicated to solve by hand. So like, are we on use MATLAB?
What do you mean by get a very big derivative? I think we have done some.
Because in the lectures,
It's not.
because for the assignment, the equation is C bs plus k on ms squared plus bs plus k. Yeah, so we have a complex numerator. So if we find the modulus for that, there's a modulus on the top and then one on the bottom, and then when we differentiate using quotient rule, like you get a very, very long derivative. It's hard to solve. So can we just use MATLAB for that, or?
You just differentiate with one variable, right?
So-
It is not difficult.
But we get like omega to the 6 and then everything else.
Yeah, it can be.
How do we solve that?
What do you mention? This kind of equations, if you got our omega 6, right? So it must be something omega 3. Okay. So we substitute.
Okay.
right? So you complete the squares.
Oh,
Okay, you find it.
yeah.
That,
Yeah, makes
you,
sense.
there's an example in the lecture notes or in the tutorial exercise. How to solve this kind of problem.
But only gives like but only says, I looked at notes, but only gives like an estimate. It's not really accurate.
One important thing is that try to find out, right, or try to devise your calculus. So if you have a differential x, y, z, right, and then you differentiate something,
Yeah.
how is that?
Depending what we're differentiating with regards to.
This is a chain. So we do it step by step. Break it down. Tx, dt, and then you break 3x, y, z, dx, and then dx, dt. And we can break it down. The trajectory over the chain. So for a complicated thing, you break it down into small parts. Then you can Okay, let us continue. So we want to see how the system responds to a control input, right? How system to control input. If the initial state is not zero, that is, the x0 is not zero, it has something. So from the equation, the x dot ax plus b u, and then if we take the Laplace transform, then we have s x of s minus x0 equals a x of s plus b u of s. Then we have a si minus a of xs equals x0 plus b. So the static response is si minus a inverse times the initial state, and then the response due to input. So this part is a response due to input, and this part is response due to initial state. Or we call it the initial condition. And then what we observe from this is that the matrix is I minus A inverse. Okay, the inverse of a matrix is also a matrix. Right. So this means plays a critical role. It plays a critical role in our system response. So we define this and then especially we define and then inverse Laplace transform. So that is the so we define a matrix, right? It is the Laplace. It is the inverse Laplace transform of the inverse of this matrix. And then we call this the transition matrix. Okay, it is also called the fundamental matrix. So here we have from the space equations, we construct is I minus A, and then invert and then we inverse Laplace transform, and that is our transition matrix. Okay, get the concept here. Okay, any question up to here? So from our previous example, right? From the water tank, okay. State space equations. Then we have A equals minus 1, 1, and 1 minus 2. Then we have the matrix Si minus A equals S plus 1. Then the determinant of this matrix so it is S plus 1, S plus 2, then minus 1, minus 1. Okay, so it is S squared plus 3S plus 1 for this example. So suppose we can factorize So we can factorize this. Then the inverse is so we must have the determinant here as the denominator. And then if we carry out calculating the minor, the cofactor, and the adjoint matrix, right, we will arrive at this equation. So this is from our minor cofactor, and then adjoint. Then we take the inverse Laplace transform. So we have it is the first row and first column element. This one we take for this element we take the inverse Laplace transform. So it gives us the exponent minus AT, and then A minus T, the exponent of the B to the T, and B minus T. That is from the inverse Laplace transform table that we can have these terms. And then for the first row, second column, and the second row, first column. Okay, for this term, the inverse Laplace transform is and then for this one, this is plus 1. This one. Okay, for this term, we have the same form, just a little bit different in the numerical value. So it is so the transition matrix we take all the factors A minus B, we take it out, this A minus B, and then the first term is S plus 2 this term. So we have E minus AT, A minus 2. And then the other term, the 1 over S plus A and S plus B, then we have and then here is the same, and then the last term is so it is a transition, it is a matrix. Yeah. Okay, this term is here. Okay, is it? Well, it is at the bottom. What? How do we get this on the right hand side? So this term goes here. So it corresponds to the first row, first column. It corresponds to the row and column of this matrix. That is from this. From this part. Okay, then what we can see from the transition matrix, so we can observe something. So at t equals 0, okay, it is the very initial instance. So exponent t to 0 is 1. So every exponent term becomes 1. So well, in this case, then exponent minus whatever t becomes 1. Then the transition matrix becomes A minus B. So this term is 1. This term is also 1. And then we have A minus B. And then the minus 2 cancels each other. Okay. So we have the A minus B. And then for the second term, the exponent is 1. And then exponent is 1. And then it is 0. This term is the same. And then it is also A minus B. So it becomes what? And then that is our, that is the initial state, the x of 0. Okay, agree with this? At time equals 0, then everything is the initial state. Okay. And then on the Okay, at the other extreme, is that when t equals infinitive, okay, that is the final or the steady state. When t goes to the infinitive, then exponent to whatever t, so it goes to 0. Goes to 1. It goes to 0. That is no matter exponential a, no matter exponential b, so they are all 0. Then the transition matrix is and then we have the a minus b and then all 0. So what we see is that the response is independent on the initial state. When time goes to infinitive. And then, of course, when the time is in between, right? So that is the transition stage. The response is the x of t, okay, equals the transition matrix, okay, and that is affected by the initial condition. Okay, any question up to here? Okay, if no question, now we consider our response to our unit step. So for unit step, we have u of s equals 1 divided by s. Then we have and then the response to the input. Okay, so it is s plus a and then s plus b, 0.1, s plus t, 1, s plus 1, and then the b matrix is 1. And then this part, the additional part, the s term, right? For this, it's the same as before, same as the initial state. Then we take the inverse Laplace transform, a little bit complicated. Okay, and then we take inverse Laplace transform. And if we do it carefully using the Laplace transform table, then we have very complicated. Okay, 2ab and then minus. And then the other element is this one. It's divided by a minus b. So this one is with the help of Laplace transform table. Otherwise, it will be very tedious to work it out by hand. Okay. So if we did with the help of Laplace transform table, it is not that difficult to obtain these two expressions. Right. The important thing is that from this expression, what we can see. So we have the analysis. So when t equals 0, so it is the very initial stage. So of course, at this stage, equals a minus b, t equals 1, because exponential 0 is 1. Then the transition matrix is and then the second element is 0. And then if we work on this, the first row, okay, we can see that the a minus b are common for the second and third term, and then if we multiply them together, we have the ab term. The ab term is also common with the first element here. Okay. So A equals 2 of AB and then minus this one. It is AB and then A minus B, the common term. So we have the A, B, and then A and B. Okay. So it is 2 A minus B. Okay. The B term here is because of the inversion by taking them together. So the numerator and then denominator cancel, and then this part also cancel, So we have the 0 and 0. So what it means is that at initial stage, input has no effect yet. So on the another case, when t equals infinity, that we have the steady state. Then e minus at equals e minus b of t. It is also 0. Then what we have is t and then a b minus 0 and then a minus b, then plus 0 and then b a minus b, and then the second term is minus b plus a, and then a minus b. So it equals to a, b, and then 1. So we say that the response to a unit step input is this one. Then that is at time goes to infinity. Then depending on the numerical value, on the numerical of a and then b, so then we can find out the actual response. Okay, then we call what is A and B. A and B. Okay, from our water tank example, we factorize the determinant into factors s plus a and s plus b. Right. Okay, we recall that S plus A, S plus B equals the determinant of Si minus A. And then we see that the system response depends on A and B. So the question is, can we change or specify A and B in controller design? Controller design. Okay, and then we also recall that a system can be configured in a feedback loop. Okay. Therefore, we can change the system characteristic which indirectly changes A and B. Okay, then we can change to response as desired. Okay. Now we consider we have a system, the x dot, and then we have the x here. How do we construct a system like this? Okay, x dot equals ax plus bu. So we have plus, and then we have the a, and then we have the u input, and then multiply b, this. And then if we have the C matrix, and then that is our Y output. Okay, up to here, this block diagram seems very familiar. We just went through it last week. Right. And then you can also put it into another form, which is the same form. Is that we have the system. We have this system. And then we have the C, and then we have the Y, and then this is the X. And then we can do it this way. This is the input. And then we have the feedback. Then we have to determine, so what should be values of K. Right? Then I think, or I'm afraid that we do not have sufficient time to go into this detail of this method, right? We'll leave it to the Friday lecture. And then we stop here. Let's stop here for today.
When we find the inverse of the SI minus A matrix, if it was a 2 by 2 matrix, could we skip to the end with the formula? Yeah. I haven't included the determinant here, but it should be open like this. That the inverse of any 2 by 2 matrix is this. Could I skip directly to here? Without having to stop.
You mean from this to this
Yeah.
point?
Yeah, without using a minor factor.
It only applies in the 2 by 2.
Yeah. Right. Would we expect a 3 by 3? But yeah, I just wanted to make sure. Thank you.
So just wanted to double check. So even if the report goes over the page limit, it's not like marks won't get deducted. So what's the page limit sort of there for? Is it for like a minimum?
Reasonable.
Right. Okay. So even if it goes over, it's okay. Is that right?
So fix is what I get.
Yeah.
Using the sample solution.
Right.
This way.
Yeah.
Right. The figures are rather large, right?
Yeah.
So if you put into 3 figures in a row, you can finish it.
Well, yeah, because I'm using LaTeX, so the writing is big, and also I'm doing all the.
You can.
I'm also doing all the derivations.
So this is the latest.
Oh yeah,
right?
I
You can
increased the
change
margin size. Yeah, I already have. It's just because I'm doing all the derivations myself,
good.
so
Good.
so it's okay if it's longer.
Okay.
Yep.
I can assure you that no marks will be deducted because of the page limit.
Okay.
Right?
Okay.
It's
All right.
not reasonable.
Okay. Good. Thank you.